Have you ever tried to imagine what our planet looked like when every single piece of land you've ever known was crammed together into one colossal landmass? Picture this for a moment. No Atlantic Ocean separating Europe from America. No Mediterranean Sea dividing Africa from Europe. Instead, imagine being able to walk from New York to London, from Cairo to Sydney, from Tokyo to Rio de Janeiro, without ever seeing a drop of ocean water. This isn't some fantasy scenario. This was reality on Earth roughly 300 million years ago, during an era when our planet's geography was so radically different that it would be completely unrecognizable to us today. Welcome to the incredible world of Pangea, the ultimate supercontinent that dominated our planet for over 160 million years. I'm absolutely thrilled you've decided to join me on this mind-bending journey back through deep time to explore one of the most fascinating chapters in Earth's geological story. Before we dive headfirst into this ancient world, I'd love to know where you're watching from right now and what you think Earth might have looked like during this extraordinary period. And if you're enjoying this deep dive into our planet's incredible past, a like would mean the world to me. And don't forget to subscribe for more incredible journeys through Earth's history. Now, here's what makes tonight's exploration particularly jaw-dropping. We're not just talking about a simple rearrangement of familiar continents. We're talking about a world where the fundamental rules of climate, weather patterns, and even life itself operated on principles so extreme and so alien that they challenge everything we think we know about how planets function. This is the story of Earth's boldest geological experiment, and the results were nothing short of spectacular and terrifying in equal measure. Let me paint you a picture that will completely reshape how you think about our planet's past. Imagine standing on a mountaintop somewhere in what we now call Colorado. But instead of looking west toward California and the Pacific Ocean, you're staring across thousands upon thousands of miles of uninterrupted land stretching all the way to what would one day become the heart of Asia. Turn around and look east, and that same continuous landmass extends through what we know today as the Atlantic coastline. Across the entire European continent and deep into the regions that would eventually become Africa and beyond. This wasn't just a larger version of any continent we know today. Pangea was a beast of geological proportions that occupied roughly 1/3 of Earth's entire surface. To put that in perspective, if you combined North America, South America, Europe, Asia, Africa, Australia, and Antarctica into a single landmass, you'd still barely comprehend the sheer scale of what we're talking about. This supercontinent was so massive that its interior regions were thousands of miles away from the nearest ocean, creating environmental conditions that were more extreme than anything we see on our planet today. But here's where things get really wild. The rest of Earth wasn't covered by multiple oceans like we have today with our Pacific, Atlantic, Indian, and Arctic waters. Instead, there was essentially one gigantic ocean called Panthalassa that surrounded this megacontinent. Picture an ocean so vast that it made our current Pacific Ocean look like a small lake in comparison. This single body of water wrapped around Pangea like a planetary embrace, creating weather systems and ocean currents that operated on scales we can barely imagine. The very shape of Pangea tells us something profound about just how alien this world really was. Rather than being a neat, compact circle of land, the supercontinent was twisted into a bizarre C shape, almost like a massive horseshoe stretched across the planet from pole to pole. Within the arms of this C-shaped landmass sat another body of water called the Tethys Ocean, a warm sea that played a crucial role in determining climate patterns across the entire supercontinent. Now, you might be wondering how on earth something this massive could even come together in the first place. The story begins around 335 million years ago, and it's a tale of continental collision that makes our modern earthquakes look like gentle tremors. Picture enormous continental plates, each carrying entire future continents, moving toward each other with inexorable force driven by convection currents deep within Earth's mantle. In the northern regions, there was a continental mass called Laurasia that included what would eventually become North America, Greenland, Europe, and northern Asia. Meanwhile, in the southern hemisphere, another massive continent called Gondwana stretched across vast areas that would one day be South America, Africa, Antarctica, Australia, and India. These weren't just random chunks of rock drifting aimlessly through ancient seas. They were colossal plates of continental crust being pushed and pulled by forces so immense they dwarf anything we experience in our modern world. When these continental giants finally collided around 320 million years ago, the impact created something that defies easy description. Imagine two cosmic freight trains, each the size of a modern continent, smashing into each other at geological speeds. The collision zone erupted into mountain ranges so massive and so tall that they made today's Himalayas look like rolling hills. These weren't ordinary mountains by any stretch of the imagination. The central Pangean mountain range that formed from this continental smash-up stretched like a massive spine through the heart of the supercontinent, reaching heights that rivaled our tallest modern peaks, but extending for thousands upon thousands of miles. Picture a mountain chain that made the Rocky Mountains, the Alps, and the Andes combined look like minor geographical features. These peaks rose during the collision and reached their maximum height around 295 million years ago, creating a continental divide that influenced weather patterns across the entire supercontinent. But the mountains were just the beginning of Pangea's extraordinary geography. The sheer size of this landmass created climate conditions that were so extreme they pushed the boundaries of what we consider possible for a habitable planet. The interior regions of Pangea became something like a continental-scale desert. But not just any desert. We're talking about arid zones so vast and so extreme that they likely represented some of the most extensive and harsh desert systems in Earth's entire geological history. Imagine the Sahara Desert, but instead of covering just a portion of northern Africa, picture it stretching across an area larger than all of modern Asia combined. The temperatures in these interior regions swung between extremes that would make Death Valley's climate seem pleasant and moderate. Scorching hot days that could literally kill most modern life forms were followed by nights so frigid that even tropical regions experienced near freezing temperatures. But here's the million-dollar question. Why were these interior regions so impossibly dry and extreme? The answer lies in a weather phenomenon that sounds almost too dramatic to be real, but geological evidence proves it existed. Welcome to the world of the Pangean mega-monsoon, a planetary-scale weather system so powerful it controlled the climate of an entire supercontinent. During the northern hemisphere's summer months, when Earth's axial tilt directed the most intense solar radiation toward the northern part of Pangea, this massive landmass would heat up like a continental-scale oven. We're talking about enormous areas of rising hot air and low-pressure zones across regions that encompass what we now call North America, Europe, and Northern Asia, all at once. Meanwhile, the southern hemisphere remained relatively cooler, creating temperature differences that drove wind patterns on a scale we can barely comprehend today. Moisture-laden air from the surrounding Panthalassa Ocean would rush toward these superheated northern regions like atmospheric rivers, bringing massive amounts of precipitation to coastal areas. But here's the critical part that made Pangea's climate so uniquely extreme. By the time these weather systems penetrated deep into the continental interior, traveling thousands of miles from any ocean, they had already dumped every drop of their moisture content. The result was that the heart of Pangea became a rain shadow zone of truly epic proportions. Then, during the northern hemisphere's winter, this entire system would reverse direction. The southern regions would heat up and the winds would shift, carrying moisture toward the southern parts of the supercontinent, while leaving northern regions in a state of extreme drought. This created seasonal variations so intense that parts of Pangea would swing between monsoon-like flooding and bone-dry desert conditions within the span of just a few months. We're talking about environmental swings so dramatic that they left permanent signatures in rock formations that geologists can still read today, more than 250 million years later. The effects of this mega-monsoon system were visible across the entire supercontinent through geological evidence that shows enormous seasonal variations in rock formation. Layers that record periods of intense flooding alternate with deposits that could only form under desert conditions. These weren't subtle changes that required sophisticated scientific instruments to detect. These were environmental transformations so extreme and so rapid that they fundamentally shaped the geological structure of entire regions. What makes this story even more remarkable is how Pangea's climate evolved over its incredibly long lifespan. This supercontinent dominated our planet for an astounding 160 million years, from its initial assembly around 335 million years ago until it began breaking apart around 175 million years ago. During this vast span of time, Earth's climate went through several distinct phases, each more extreme than anything we experience in our modern world. During the late Carboniferous period, when Pangea was still in the process of forming, much of the supercontinent was covered in vast swamp forests that stretched across areas the size of modern continents. These weren't ordinary wetlands by any measure. Picture tropical rainforests filled with primitive trees and giant ferns, all thriving in a greenhouse climate that had absolutely no modern equivalent. But as Pangea reached its full extent during what geologists call the Permian period, roughly 295 to 252 million years ago, the climate became increasingly extreme in ways that challenge our understanding of planetary climate systems. The interior regions dried out even further, while the mega-monsoon system reached its maximum intensity, creating what paleoclimatologists describe as the most continental climate in Earth's entire geological history. This was a world without polar ice caps, where even the Arctic and Antarctic regions remained unfrozen year-round. Yet paradoxically, it was also a world where vast interior regions experienced temperature swings that would have been lethal to most modern forms of life. Days in the interior deserts could reach temperatures that made modern desert extremes seem mild, while nights would plunge toward freezing, even in what should have been tropical latitudes. The plant life that managed to survive in this harsh environment was unlike anything we see on Earth today. The giant swamp forests of the earlier periods gave way to tougher, more resilient vegetation as conditions became increasingly challenging. Gymnosperms, the ancestors of our modern conifers, began to dominate the landscape with sophisticated water conservation strategies that allowed them to survive in increasingly arid conditions. On the ground level, carpets of moss and primitive ferns created miniature ecosystems around the bases of these early conifers, forming complex relationships that helped entire plant communities survive the brutal seasonal extremes. But these weren't the lush, stable forest communities we might imagine. These plant communities were constantly battling against environmental conditions that would challenge even our most specialized desert plants today. The animal life that called this extreme world home was equally extraordinary and equally adapted to conditions that seem almost impossible by modern standards. This was the golden age of creatures called synapsids, the mammal-like reptiles that dominated terrestrial ecosystems long before dinosaurs ever set foot on our planet. These weren't small, insignificant creatures hiding in the shadows of larger predators. Many synapsids were formidable, sophisticated animals that had evolved complex social behaviors and advanced temperature regulation strategies. The most famous of these ancient creatures was Dimetrodon, a fearsome predator that looked like something straight out of a science fiction movie. Despite its distinctly lizard-like appearance, Dimetrodon was actually more closely related to mammals than to modern reptiles. Its most striking feature was a massive sail-like fin that rose from its back like a prehistoric solar panel, probably used for temperature regulation in Pangea's extreme climate conditions. These remarkable animals had to cope with environmental challenges that would overwhelm even our most specialized desert wildlife today. The seasonal temperature swings that could range from scorching to near freezing, the extreme aridity of interior regions, and the unpredictable nature of the mega-monsoon system created evolutionary pressures unlike anything life on Earth had encountered before or has encountered since. But all of this incredible life, all of these extraordinary adaptations, all of the complex ecosystems that had spent millions of years learning to thrive in Pangea's harsh conditions, were about to face the ultimate test of survival, around 252 million years ago, at the end of what geologists call the Permian period, something happened that would change the course of life on Earth in ways that still echo through our planet's biology today. The event that unfolded has earned the ominous nickname the Great Dying, and it would prove to be the most catastrophic extinction event in our planet's entire history. We're talking about a biological catastrophe so severe that it makes the extinction of the dinosaurs look relatively minor by comparison. More than 95% of marine species would vanish from the fossil record. More than 70% of land animals would disappear entirely. The world that had existed during Pangea's peak was about to end in a way that nearly brought all life on Earth to a complete standstill. What could possibly cause such unprecedented devastation across an entire planet? The answer involves volcanic eruptions so massive they make our most devastating modern volcanic disasters look like gentle fireworks displays. We're talking about climate changes so severe they pushed Earth's environmental systems beyond their breaking points. And most remarkably, we're talking about a recovery process that would take millions upon millions of years to complete. The scale of what was about to unfold across Pangea defies easy comprehension, but let me try to paint you a picture that captures just how extreme this event really was. Imagine if every single volcano on Earth today erupted simultaneously in perfect coordination. Now, multiply that catastrophe by a factor of hundreds, and you still wouldn't fully capture the sheer magnitude of what began around 252 million years ago in a region that we now call Siberia. The Siberian traps represent one of the most violent and sustained geological events in Earth's recorded history. These weren't ordinary volcanic eruptions that lasted for days, weeks, or even months. We're talking about flood basalts, massive outpourings of lava that covered an area roughly two-thirds the size of the modern United States and continued erupting for potentially hundreds of thousands of years. The total volume of molten rock that poured across the landscape reached somewhere between 1 and 4 million cubic kilometers. To put that in perspective, that's enough lava to bury the entire continental United States under a layer of molten rock several hundred feet deep. But as devastating as that sounds, the lava itself was only the beginning of this planetary catastrophe. The volcanic gases released during these eruptions fundamentally altered Earth's atmosphere and climate in ways that pushed the planet's environmental systems to their absolute breaking points. Massive quantities of carbon dioxide, sulfur compounds, and other toxic gases billowed into the atmosphere, creating a greenhouse effect so intense it made Pangea's already extreme climate seem moderate by comparison. The timing of these eruptions was devastatingly precise in the worst possible way. Recent scientific research has shown that the Siberian flood basalts began at almost exactly the same moment as the Great Dying Extinction event, providing compelling evidence that these volcanic outpourings were the primary trigger for the greatest biological catastrophe in Earth's history. Picture what this meant for the already stressed ecosystems of Pangea. The supercontinent's interior regions, which had been struggling with extreme aridity and temperature swings for millions of years, suddenly faced conditions that were beyond the tolerance limits of virtually all terrestrial life. The carefully balanced plant communities that had taken millions of years to adapt to Pangea's harsh climate were overwhelmed by environmental changes happening faster than evolution could possibly respond. The effects rippled through every level of the ecosystem like a biological domino effect. The gymnosperm forests that had covered parts of the supercontinent began to die off as temperatures soared beyond survivable levels, and acid rain created by volcanic sulfur compounds poisoned the soil. The delicate balance that had allowed complex food webs to exist in Pangea's challenging environment collapsed within what may have been as little as 100,000 years, which is essentially instantaneous in geological terms. The fossil evidence from this period tells a story of almost complete ecological collapse that reads like a planetary horror story. Rock layers from the late Permian period show abundant signs of diverse plant communities, with fossil remains of the conifer forests that had blanketed many regions of Pangea for millions of years. But the early Triassic layers that follow tell a completely different and much more disturbing story. Instead of the usual plant fossils that characterize healthy ecosystems, these rocks are dominated by the remains of fungi. These are organisms that thrive in the aftermath of ecological disasters as they feed on the vast quantities of decaying organic matter left behind by environmental catastrophes. The dominance of fungal remains in the rock record suggests that Pangea's landscapes were literally carpeted with the remains of dead plants and animals for millions of years, following the Great Dying. For the animal life of Pangea, this extinction event represented an existential crisis unlike anything life on Earth had ever faced before. The synapsids, those remarkable mammal-like reptiles that had dominated terrestrial ecosystems for millions of years, saw their populations decimated on a scale that's difficult to comprehend. Dimetrodon and its relatives, the apex predators that had ruled Pangea's food webs for so long, vanished from the fossil record entirely. The large herbivorous synapsids that had grazed in the gymnosperm forests disappeared as well, leaving behind ecosystems that were almost completely empty of large terrestrial vertebrates. But the marine ecosystem surrounding Pangea suffered even more catastrophic losses that pushed ocean life to the very brink of complete extinction. The warm Tethys Ocean, which had harbored incredible diversity during the Permian period, became something approaching a biological wasteland. More than 95% of marine species went extinct, transforming the ocean from a vibrant ecosystem teeming with life into something that resembled a nearly sterile sea. But perhaps the most remarkable aspect of this catastrophe wasn't the devastation itself, as terrible as it was. It was what happened next. The Great Dying marked not just the end of one chapter in Earth's history, but the beginning of an entirely new one. The Triassic period that followed would see life experiment with completely new forms and strategies, ultimately giving rise to some of the most successful animals ever to walk our planet. The early Triassic world was a desolate, largely empty place that would have seemed almost alien to us today. The first few million years after the extinction were characterized by what paleontologists call the Cold Gap, a period when virtually no coal deposits formed anywhere on Earth. This absence of coal reflects the near-complete collapse of terrestrial plant communities across the entire planet. Without thriving forests to create the organic matter that eventually becomes coal, the rock record from this period is remarkably barren of the carbon-rich deposits that characterize healthier geological eras. Current estimates suggest it may have taken up to 10 million years for Earth's ecosystems to recover from the devastation of the Great Dying. That's a recovery period longer than the entire span of time since the extinction of the dinosaurs. During those long millennia of recovery, Pangea remained a largely empty stage, waiting for new evolutionary actors to emerge and fill the ecological roles left vacant by the Permian extinction. When recovery finally began, it was unlike anything that had come before in Earth's history. The surviving plant species began to diversify and spread across Pangea's devastated landscapes, but they were doing so in a world that had been fundamentally transformed by the extinction event and the continuing after effects of those massive volcanic eruptions. The climate remained extreme by any standard we might use today, but life began adapting to these harsh new conditions in ways that would reshape the very foundations of terrestrial biology. As plant communities slowly re-established themselves across the supercontinent, they created opportunities for animal life to return to environments that had been essentially lifeless for millions of years. But the creatures that emerged from this recovery process were dramatically different from their Permian predecessors. The synapsids, while not completely extinct, never managed to regain the dominant position they had held for so long. Instead, a completely new group of reptiles began to diversify and experiment with revolutionary body plans and ecological strategies. These were the archosaurs, and they would eventually become the ancestors of some of the most successful animals in Earth's entire history. During the early stages of Triassic recovery, these archosaurs were small, relatively insignificant members of the slowly recovering ecosystems, but they possessed certain biological advantages that would prove absolutely crucial in the changing world of post-extinction Pangea. The climate during the Triassic period remained extreme by modern standards, but it was also remarkably stable compared to the chaotic environmental conditions that had characterized the Great Dying. The absence of polar ice caps meant that temperature gradients from equator to pole were actually less extreme than they are today, creating a more uniform global climate that, while harsh, was at least predictable. This stability, combined with the vast ecological opportunities created by the extinction, provided ideal conditions for evolutionary experimentation on a scale that had never been possible before. Around 240 million years ago, something truly extraordinary appeared in the fossil record that would change the course of life on Earth forever. These were small, bipedal creatures with elongated hind limbs and relatively large brains for their body size. They moved with a distinctive gait, running on 2 legs rather than 4, and showed evidence of sophisticated behavioral adaptations that set them apart from anything that had come before. These were the first dinosaurs, and they were about to begin one of the most successful evolutionary radiations in our planet's entire history. The earliest dinosaurs weren't the massive, imposing creatures that would later dominate Mesozoic ecosystems and capture our modern imagination. Instead, they were relatively small, agile animals that probably weighed no more than a few dozen pounds. But what they lacked in size, they more than made up for in adaptability, intelligence, and evolutionary potential. These early dinosaurs possessed several key advantages that allowed them to thrive in the recovering ecosystems of Triassic Pangea. Their bipedal locomotion gave them significant speed and agility advantages over many of their contemporaries, who were still relying on four-legged movement. Their relatively large brains allowed for sophisticated behavioral adaptations, including potentially complex social behaviors and advanced hunting strategies that gave them edges in the competitive world of post-extinction recovery. Perhaps most importantly, their physiology was remarkably well suited to the extreme climate conditions that still characterized much of Pangea during the Triassic period. Their efficient respiratory systems and advanced temperature regulation capabilities allowed them to remain active and competitive, even in the harsh environmental conditions that continued to challenge most other forms of life. One of the most successful early dinosaurs was Colossal, a slender predator that first appeared around 225 million years ago. Despite weighing only 40 to 50 pounds, Colossal was a formidable hunter equipped with razor-sharp teeth, powerful grasping claws, and hollow bones that gave it a lightweight build perfectly optimized for quick, agile movement through Pangea's recovering landscapes. The hollow bones that give Colossal its name, meaning hollow form, represented an evolutionary innovation that would become characteristic of all later dinosaurs and would eventually allow some species to grow to absolutely enormous sizes while maintaining relatively efficient locomotion. This structural adaptation was just one example of the remarkable biological innovations that were emerging during the Triassic recovery. Coelophysis and its relatives fed on a diverse array of prey, including small reptiles, early mammals, and possibly insects, and other arthropods that were also recovering from the extinction event. Their hunting strategies were likely quite sophisticated, potentially involving pack behaviors and coordinated attacks on larger prey animals. Fossil evidence suggests that some early dinosaurs may have been capable of complex social interactions, with group living arrangements that provided significant advantages in both hunting efficiency and protection from the various predators that shared their recovering ecosystems. But dinosaurs weren't the only remarkable success story of the Triassic recovery period. Around the same time that the first dinosaurs were establishing themselves in terrestrial ecosystems across Pangea, another group of animals was quietly beginning its own extraordinary evolutionary experiment. These were the first true mammals, tiny creatures that looked somewhat like modern shrews, but represented a completely revolutionary approach to vertebrate biology. The earliest mammals were incredibly small, perhaps no larger than a modern mouse, and they lived in the shadows of the larger reptiles that were beginning to dominate Triassic ecosystems. But despite their diminutive size, they possessed several revolutionary adaptations that would eventually prove crucial to their long-term evolutionary success. They were warm-blooded, meaning they could maintain constant body temperatures regardless of environmental conditions, giving them a significant advantage in Pangea's still extreme climate. They had developed fur for insulation, allowing them to remain active during the cool nights that characterized even tropical regions of the supercontinent. Most remarkably of all, they produced milk to nourish their young, providing their offspring with nutritional and immunological advantages that would prove absolutely crucial in the competitive world of post-extinction recovery. One of the earliest known mammals was Morganucodon, a creature about the size of a modern shrew that still laid eggs like its reptilian ancestors, but fed its young with milk after they hatched. This fascinating combination of reptilian and mammalian characteristics provides us with an incredible window into the evolutionary transition that was occurring during the Triassic period, showing us how life was experimenting with entirely new biological strategies. The coexistence of early dinosaurs and early mammals during the Triassic period established one of the most important ecological relationships in Earth's history. For the next 160 million years, these two groups would evolve alongside each other, with dinosaurs generally dominating the large-bodied terrestrial niches, while mammals remained primarily small, nocturnal, and specialized for ecological roles that didn't directly compete with their reptilian contemporaries. The plant communities that supported these recovering animal populations were also undergoing dramatic changes during the Triassic period. The gymnosperms that had managed to survive the Great Dying began diversifying into new forms that were much better adapted to the post-extinction world that was emerging across Pangea's landscapes. Conifers became increasingly dominant in many regions, their sophisticated water conservation adaptations serving them exceptionally well in the still arid interior regions of the supercontinent. Alongside these conifers, other gymnosperm groups began to flourish in ways they never had before. Cycads, with their distinctive palm-like appearance, became common in many tropical and subtropical regions. Ginkgos, represented today by only a single surviving species, were diverse and widespread during the Triassic, creating forest communities unlike anything we see in our modern world. These plant communities created the ecological foundation for the complex food webs that would eventually characterize the later Mesozoic era. The recovery of Triassic ecosystems was also marked by the return of sophisticated marine life to the oceans surrounding Pangea, the Tethys Ocean, which had been largely sterilized by the Great Dying, slowly began to support new communities of marine reptiles, fish, and invertebrates. Some of these marine reptiles grew to enormous sizes, filling ecological niches that had been completely vacant since the extinction event. These ocean giants represented entirely new experiments in marine predation and would eventually give rise to some of the most spectacular marine reptiles in Earth's history. As the Triassic period progressed and life continued to recover and diversify across Pangea's vast expanse, the geological forces that had originally created the supercontinent were beginning to shift and change. The same powerful tectonic processes that had brought all the continents together were starting to pull them apart again, setting the stage for the next great chapter in Earth's geological and biological history. Deep beneath Pangea, new patterns of mantle convection were creating stresses and pressures that would eventually tear the supercontinent into fragments, creating the continental configuration that would eventually lead to our modern world. The first signs of this impending breakup appeared around 200 million years ago, near the end of the Triassic period. Rift valleys began forming in what would eventually become the Atlantic Ocean, and volcanic activity increased dramatically along these developing fracture zones. The great experiment of Pangea was beginning to reach its end, but its profound effects on life would continue to influence evolution for hundreds of millions of years into the future. The extreme environmental conditions, the devastating mass extinction, and the remarkable recovery had fundamentally altered the trajectory of life on our planet in ways that continue to shape the biological world we see today. The breakup of Pangea wasn't some sudden catastrophic event that happened overnight, like a massive earthquake splitting the ground beneath your feet. Instead, this was geology operating on its own timescale, a slow-motion dissolution that would unfold over tens of millions of years and completely transform our planet's entire geography. Picture enormous rivers of molten rock flowing through Earth's interior, driven by temperature differences that created circulation patterns spanning thousands of miles across our planet's depths. These massive mantle currents had been responsible for pushing all those ancient continents together to form Pangea in the first place. But now, like some gigantic geological clock reaching the end of its cycle, they were shifting direction and creating new upwelling zones that would eventually pull the supercontinent apart piece by piece. The first subtle signs of this impending breakup appeared as changes in volcanic activity across different regions of Pangea around 220 million years ago. Geologists today can detect evidence of increased volcanic activity in areas that would eventually become the boundaries between separating continental fragments. These weren't the massive world-ending volcanic eruptions that had caused the Great Dying. Instead, they were more localized volcanic events that created linear chains of eruptions, like geological breadcrumbs marking the path that would eventually split the supercontinent. The process began in what would eventually become the Central Atlantic region, along a line running roughly between what we now recognize as eastern North America and northwestern Africa. Deep beneath this zone, rising columns of superheated mantle material began creating bulges in the overlying continental crust. These thermal domes stretched and weakened the solid rock above them, creating the first hairline fractures that would eventually widen into the Atlantic Ocean basin. But here's what makes this story absolutely fascinating. The breakup of Pangea wasn't simply a matter of the continent cracking apart like a piece of pottery dropped on a stone floor. This was a far more complex process that involved fundamental changes in how Earth's entire tectonic system operated. As the supercontinent began to fracture, it created opportunities for entirely new patterns of ocean circulation to develop across our planet. These changing oceanic currents would have profound effects on global climate patterns, potentially influencing the very evolutionary processes that were continuing to shape life across the fragmenting landmass. The timing of Pangea's initial breakup coincided with another significant extinction event, though thankfully not nearly as severe as the great dying that had ended the Permian period. The Triassic-Jurassic extinction event occurred around 201 million years ago and eliminated roughly 20% of marine families while having significant impacts on terrestrial ecosystems as well. While scientists continue to debate the exact cause of this extinction, many believe it was directly related to the massive volcanic activity associated with something called the Central Atlantic Magmatic Province, one of the largest volcanic events in our planet's entire geological history. This volcanic activity was directly connected to the early stages of Pangea's breakup. As the continental crust began stretching and thinning along the developing rift zones, it created pathways for enormous quantities of magma to reach the surface. The resulting eruptions covered vast areas of what would become eastern North America, western Africa, and parts of South America, with thick layers of volcanic rock. The environmental effects of these eruptions were severe but more localized than the global catastrophe that had ended the Permian period. For the complex ecosystems that had developed during the Middle and Late Triassic period, this extinction event represented another major disruption, but also created new opportunities for evolutionary innovation and experimentation. Many of the sophisticated ecological relationships that had developed during the Triassic recovery were severed by this extinction, but the surviving species found themselves in a world filled with vacant ecological niches, just waiting to be explored and exploited. The dinosaurs, which had already established themselves as successful and diverse components of Triassic ecosystems, were among the groups that weathered this extinction event relatively well. In fact, the Triassic-Jurassic extinction may have actually benefited dinosaur evolution by eliminating some of their key competitors and opening up entirely new ecological opportunities. Many of the advanced synapsid lineages that had managed to coexist with dinosaurs during the Triassic period were eliminated during this extinction, leaving dinosaurs as the dominant large terrestrial vertebrates for the very first time in Earth's history. As Pangea entered what geologists call the Jurassic period around 200 million years ago, the supercontinent was beginning to show clear signs of its impending fragmentation. The rift valleys that had begun forming during the late Triassic were deepening and widening, creating long, narrow basins that would eventually become ocean floors. But this process was still in its early stages, and most of Pangea remained connected as a single massive landmass. The climate during the early Jurassic period was significantly different from the extreme conditions that had characterized much of the Triassic. As the rift systems developed and the first narrow seaways began forming between separating continental fragments, they created new pathways for ocean water to penetrate into the interior regions of the supercontinent. This had a moderating effect on the extreme continental climate that had dominated Pangea during its peak extent. The mega-monsoon system that had created such dramatic seasonal variations during the Triassic period began to weaken as the geography of the supercontinent started changing. The development of rift valleys and early seaways created new sources of moisture for interior regions that had been almost completely arid during earlier periods. This climatic moderation had profound effects on both plant and animal communities across Pangea's vast expanse. Plant communities that had been restricted to coastal regions during the Triassic period began expanding into interior areas as conditions became more hospitable. The gymnosperm forests that had developed sophisticated adaptations to extreme aridity found themselves in a world where water stress was less severe and growing seasons were more predictable. This allowed for the development of more complex forest ecosystems, with greater structural diversity and more extensive food webs than had been possible during the harshest periods of Pangea's existence. The changing climate also created new opportunities for animal communities to develop and flourish in ways that hadn't been possible before. The harsh interior regions that had supported only highly specialized desert-adapted species during the Triassic period became accessible to a much broader range of organisms. Migration routes that had been impossible during the height of Pangea's aridity became viable, allowing for greater mixing of populations and accelerated evolutionary change across the supercontinent. The dinosaurs that had survived the Triassic-Jurassic extinction began diversifying rapidly during the early Jurassic period. The reduced competition from other vertebrate groups, combined with the expanding range of habitable environments, created absolutely ideal conditions for dinosaur evolution to explode in new directions. New lineages appeared that experimented with dramatically different body sizes, dietary strategies, and ecological roles. Some of the most significant developments during this period involved the evolution of the first truly gigantic dinosaurs. The sauropods, which would eventually become the largest land animals ever to exist on our planet, first appeared during the early Jurassic period. These weren't simply larger versions of earlier herbivorous dinosaurs that had come before them. They represented fundamentally new approaches to vertebrate biology, with body plans and physiological systems that had absolutely no precedent in earlier terrestrial animals. The evolution of giant sauropods had cascading effects throughout Jurassic ecosystems that transformed entire landscapes. Their feeding activities could alter entire environments, creating clearings in forests and changing patterns of plant succession across vast areas of the fragmenting supercontinent. Their sheer size made them largely immune to predation once they reached adulthood, allowing them to exploit food resources that were completely unavailable to smaller herbivores. The success of these giant herbivorous dinosaurs during the Jurassic period also drove the evolution of larger and more sophisticated predators. The first truly massive theropod dinosaurs appeared during this time, developing the size and strength necessary to potentially threaten even adult sauropods. These predator-prey relationships created some of the most dramatic ecological dynamics in our planet's entire history. But the most significant aspect of Jurassic dinosaur evolution wasn't just the evolution of these gigantic forms that capture our imagination today. It was the incredible diversity of ecological strategies that different dinosaur lineages began exploring across Pangea's changing landscapes. Some groups became highly specialized for aquatic or semi-aquatic lifestyles, developing adaptations that allowed them to exploit the expanding network of Rift Valley lakes and early seaways that were beginning to fragment the supercontinent. Others evolved sophisticated social behaviors, with evidence suggesting that some species lived in large herds with complex social structures that rivaled those of modern mammals. The plant communities of the Jurassic period were also undergoing significant changes in response to these evolving herbivore communities. The intense grazing pressure created by large dinosaur herds drove the evolution of new defensive strategies in plants that pushed the boundaries of botanical innovation. Some species developed chemical defenses so sophisticated they could actually adjust the toxicity of their tissues in response to herbivore pressure, creating a kind of biological arms race between plants and the animals that fed on them. Others evolved rapid growth strategies that allowed them to recover quickly from grazing damage and continue thriving even under intense herbivore pressure. Perhaps most remarkably, some plant communities began developing what can only be described as collaborative relationships with dinosaur herbivores. Certain conifer species appeared to actually benefit from moderate browsing pressure, which cleared competing vegetation and created ideal conditions for their seedlings to establish themselves. These plants began producing cones and seeds that were specifically adapted for dispersal by large dinosaurs, creating some of the most sophisticated plant-animal partnerships in prehistoric ecosystems. The complexity of these ecological relationships was reaching levels that hadn't existed before the Great Dying, and wouldn't be seen again until much later in Earth's history. Different species weren't just coexisting in the same environments anymore. They were developing intricate webs of interdependence that made entire ecosystems more resilient and productive than the sum of their individual parts. This biological complexity was creating feedback loops that accelerated evolutionary innovation across the fragmenting supercontinent. The marine ecosystems surrounding Pangea were experiencing equally dramatic changes as the supercontinent began its slow breakup. As rift valleys deepened and began flooding with seawater, they created entirely new marine environments that were unlike anything that had existed during Pangea's peak extent. These narrow, elongated seas had unique characteristics that fostered the evolution of specialized marine communities adapted to these specific conditions. The early Atlantic Ocean, which began forming along the rift between North America and Africa, was initially a much smaller and shallower sea than it would eventually become. But even in its earliest stages, it provided habitat for marine organisms that had been excluded from the massive Panthalassa Ocean by its sheer size and the extreme conditions along Pangea's coastlines. Marine reptiles that had survived the Triassic-Jurassic extinction began diversifying rapidly in these new marine environments. Some lineages evolved into forms that were perfectly adapted to the shallow, warm conditions of the early Atlantic. Others developed the ability to move between marine and freshwater environments, taking advantage of the complex network of rift valley lakes and rivers that connected the interior of the fragmenting supercontinent with the expanding ocean basin. The development of new seaways also had important implications for marine circulation patterns across the entire planet. As ocean water began penetrating deeper into the continental interior through the developing rift systems, it created new pathways for heat and moisture transport that had moderating effects on climate across much of Pangea. But perhaps the most significant consequence of Pangea's early breakup was the way it began isolating different continental fragments from each other. As the rift valleys widened and deepened, they created barriers to the movement of terrestrial organisms that had profound evolutionary consequences. Populations that had been connected across the supercontinent began becoming isolated on separate continental fragments. This geographic isolation would lead to the development of distinct regional faunas and floras, each adapted to the specific conditions of their continental home, setting the stage for the incredible biological diversity that would characterize the later Mesozoic era. The process of continental drift that began with Pangea's breakup would continue for millions of years, eventually creating the modern configuration of continents and oceans that we see today. But the biological consequences of this process began immediately as populations became isolated and began evolving in completely different directions. The early stages of this isolation can be seen clearly in the fossil record from different parts of the former supercontinent. Dinosaur species that appear in North American rocks from the Middle Jurassic period are increasingly different from contemporary species found in South America or Africa. This divergence reflects the early stages of evolutionary separation that would eventually produce the distinct biogeographic regions we recognize in our modern world. Picture what was happening to life during this critical transition period. As these ancient land masses drifted apart, they carried with them not just rocks and minerals, but entire evolutionary legacies that would unfold in dramatically different directions. The narrow Atlantic that was forming between North America and Africa wasn't yet the vast ocean we know today. It was more like an enormous inland sea, perhaps similar to the modern Mediterranean, but stretching for thousands of miles. This growing waterway created the first real barrier to terrestrial animal movement since Pangea's formation, and the biological consequences were immediate and profound. On the eastern side of this developing ocean, the dinosaur populations that would eventually become European and African faunas began diverging from their North American relatives. These weren't dramatic changes that happened overnight. Instead, they represented the beginning of subtle shifts in evolutionary pressure that would accumulate over millions of years. The slightly different climate conditions on each side of the widening seaway, the varying plant communities that developed in response to these conditions, and the gradual genetic isolation of populations all contributed to an accelerating pattern of biological divergence. The sauropod dinosaurs provide a fascinating window into this process of continental separation and evolutionary divergence. During the early Jurassic, these giants had been relatively uniform across Pangea, with similar species found from what is now the American Southwest to the forests of ancient Africa. But as the Atlantic widened and populations became isolated, different lineages began experimenting with different solutions to the challenges of gigantism. In North America, some sauropod lineages developed increasingly sophisticated social behaviors, with evidence suggesting they lived in massive herds that migrated across vast distances following seasonal food resources. These North American giants evolved relatively longer necks and more specialized feeding structures, adaptations that allowed them to exploit the tall conifer forests that were becoming increasingly common in the region's changing climate. Meanwhile, on the African side of the widening Atlantic, sauropod evolution took very different directions. The slightly warmer, more stable climate conditions in this region favored the evolution of even larger body sizes, but with different proportions and feeding strategies that reflected their unique environmental pressures. Some African lineages developed broader, more powerful bodies that allowed them to process tougher, more fibrous plant material. Others evolved more elongated builds that were optimized for reaching vegetation in the increasingly diverse forest canopies that were developing in their region. These weren't just minor variations on a common theme. They represented the beginning of fundamental divergences that would eventually produce sauropod lineages, so different they would be difficult to recognize as close relatives. The process of continental drift was essentially creating parallel universes of dinosaur evolution, each responding to slightly different environmental pressures and developing along unique evolutionary trajectories. The theropod dinosaurs, the carnivorous lineages that would eventually give rise to modern birds, were undergoing equally dramatic changes during this period of continental fragmentation. The isolation of populations on different continental fragments created opportunities for predator-prey arms races to develop independently in different regions. In some areas, the evolution of increasingly large herbivorous dinosaurs drove the development of massive predators capable of hunting them effectively. In other regions, the abundance of smaller prey species favored the evolution of more agile, intelligent hunters that relied on speed and cunning rather than brute force. One of the most remarkable aspects of this period was the way different continental regions began developing their own signature approaches to carnivorous dinosaur design. The theropods that were evolving in what would become North America were developing increasingly sophisticated pack hunting behaviors and advanced sensory capabilities that would serve them well in their changing environment. Some lineages were experimenting with early forms of the complex respiratory systems that would later make birds such efficient flyers. These weren't random evolutionary experiments, but rather systematic responses to the specific challenges and opportunities presented by their fragmenting world. On other continental fragments, theropod evolution was exploring completely different possibilities. Some regions saw the development of theropods with increasingly powerful jaw muscles and teeth designed for crushing bone, adaptations that allowed them to exploit carcasses more efficiently than their competitors. Others developed lineages with elongated skulls and necks, perfectly designed for fishing in the expanding network of Rift Valley lakes and early seaways that were beginning to separate the continental fragments. These aquatic adaptations represented entirely new ecological strategies that hadn't been possible during Pangea's unified existence. But perhaps the most significant development during this period wasn't related to the giant dinosaurs that tend to capture our imagination today. It was the quiet evolutionary revolution that was occurring among the smaller, more agile dinosaur lineages that would eventually give rise to birds. These creatures were developing a suite of adaptations that would prove revolutionary in ways that would reshape life on Earth forever. Hollow bones for weight reduction, increasingly sophisticated feathers for insulation and display, and most importantly, the complex respiratory and circulatory systems that would eventually make powered flight possible. The earliest evidence of feathered dinosaurs appears in the fossil record during this Middle Jurassic period, and it's clear that these structures initially evolved for purposes other than flight. The feathers of these early dinosaurs were probably used for temperature regulation in the increasingly variable climate conditions created by Pangea's breakup. Some species may have also used elaborate feather displays for communication and mate selection, behaviors that were becoming increasingly important as populations became more scattered and isolated across the fragmenting supercontinent. These social adaptations would prove crucial for maintaining species cohesion, even as geographic barriers began separating populations. The plant communities that formed the foundation of these evolving ecosystems were also undergoing dramatic transformations in response to the shifting geography and climate. The gymnosperms that had dominated Pangea's vegetation during the Triassic period were being joined by new lineages that were better adapted to the more moderate, humid conditions developing in many regions. One of the most significant botanical developments during this period was the evolution of the first flowering plants, or angiosperms. These weren't the diverse, colorful flowers we associate with modern ecosystems. The earliest angiosperms were small, relatively simple plants that looked more like modern magnolias than roses or daisies, but they possessed a revolutionary innovation that would change the face of terrestrial ecosystems forever. Enclosed seeds that were protected during development and could be dispersed more efficiently than the exposed seeds of gymnosperms. This seemingly simple adaptation gave flowering plants enormous advantages in colonizing new habitats and responding to environmental changes. The appearance of flowering plants during the Middle Jurassic period represented one of the most important evolutionary innovations in the history of terrestrial life. These plants could reproduce more quickly and efficiently than their gymnosperm contemporaries, allowing them to colonize new habitats and respond more rapidly to the environmental changes that were sweeping across the fragmenting supercontinent. More importantly, they began developing complex relationships with animal pollinators, creating entirely new categories of ecological interaction that hadn't existed before. The early pollinators weren't bees or butterflies, which wouldn't evolve until much later. Instead, they were primitive beetles and other insects that were attracted to the protein-rich pollen and nectar produced by early flowering plants. These relationships weren't as sophisticated as modern plant-pollinator partnerships, but they represented the beginning of one of the most important coevolutionary processes in Earth's history. As plants and insects evolved together, they created feedback loops that accelerated evolutionary innovation in both groups. The marine ecosystems surrounding the fragmenting supercontinent were experiencing equally revolutionary changes that would reshape oceanic life. As new ocean basins formed and existing seaways deepened, they created opportunities for marine life to experiment with ecological strategies that had been impossible during Pangea's peak extent. The relatively narrow, shallow seas that characterized the early stages of continental breakup had very different characteristics from the vast, deep Panthalassa Ocean that had surrounded the supercontinent. These new marine environments were warmer, more nutrient-rich, and more geographically complex than the open ocean. They provided ideal conditions for the evolution of diverse marine reptile communities that were adapted to specific local conditions rather than the broad, generalized strategies that had been necessary for survival in Panthalassa's immense waters. Some of the most spectacular marine reptiles in Earth's history evolved during this period of oceanic transformation. The plesiosaurs, long-necked marine reptiles that could reach lengths of over 40 feet, developed into apex predators that dominated the food webs of the expanding Atlantic and other early ocean basins. These weren't simply large aquatic lizards struggling to survive in marine environments. They were sophisticated marine hunters with advanced hydrodynamic adaptations and complex social behaviors that made them incredibly successful in their aquatic realm. Other marine reptile lineages experimented with different ecological strategies that reflected the diverse opportunities available in these new marine environments. The ichthyosaurs, dolphin-like reptiles that had first appeared during the Triassic period, continued to diversify during the Jurassic, with some species developing echolocation capabilities similar to modern dolphins and whales. The pliosaurs, short-necked relatives of the plesiosaurs, evolved into some of the most powerful marine predators ever to exist, with skulls that could exceed 6 feet in length and bite forces that rivaled those of the largest dinosaurs. These marine giants represented entirely new experiments in oceanic predation. The success of these marine reptile communities had important implications for terrestrial ecosystems as well. Many of these oceanic giants were capable of venturing into coastal waters and river systems to hunt, creating evolutionary pressures for terrestrial animals to develop new defensive strategies and behaviors. Some of the most sophisticated group behaviors and anti-predator adaptations seen in Jurassic dinosaur communities may have evolved in response to threats from these marine superpredators. The interaction between marine and terrestrial ecosystems during this period was more complex and intimate than anything we see in modern environments. The expanding marine ecosystems also created new opportunities for the evolution of flying reptiles. The pterosaurs, which had first appeared during the Triassic period, began diversifying rapidly during the Jurassic, as the expanding network of seaways and coastal environments provided ideal hunting grounds for aerial predators. Some pterosaur lineages developed wingspans that exceeded 20 feet, making them among the largest flying animals ever to exist. These giants weren't just scaled-up versions of smaller species. They had evolved sophisticated flight adaptations that included hollow bones, advanced wing membrane structures, and complex muscle arrangements that allowed them to soar efficiently over vast distances. Their success demonstrated that the airspace above Earth's fragmenting continents was becoming an increasingly important ecological frontier. Different species were exploring various aerial niches, from high-altitude soaring to low-level coastal fishing, creating a three-dimensional ecosystem that extended from the ocean depths to the upper atmosphere. As the Middle Jurassic period progressed, the effects of continental fragmentation were becoming visible in virtually every aspect of Earth's biological systems. The climate was becoming more varied and regionally distinct as different continental fragments drifted into different latitudinal zones and developed their own unique weather patterns. Ocean circulation was becoming more complex as new seaways created additional pathways for heat and moisture transport around the planet. Most importantly, the biological communities on different continental fragments were beginning to develop their own distinct characteristics that reflected their unique evolutionary histories and environmental pressures. The process wasn't uniform or predictable across the former supercontinent. Some continental fragments remained connected by land bridges for millions of years after initial rifting began, allowing continued biological exchange even as the overall supercontinent structure broke down. Other regions separated quickly and completely, leading to rapid evolutionary divergence that created entirely new forms of life. The result was a complex mosaic of connected and isolated populations that created unprecedented opportunities for evolutionary experimentation across the fragmenting land mass. In some regions, the continued connection between continental fragments allowed for the development of transcontinental migration routes that supported some of the largest animal populations in Earth's history. Fossil evidence suggests that some dinosaur species maintained continent-spanning ranges well into the Middle Jurassic period, with individual populations migrating thousands of miles, following seasonal food resources. In other areas, the rapid development of marine barriers created island-like environments where small populations became isolated and began evolving in directions that would have been impossible in larger, more connected populations. Some of these isolated communities developed into highly specialized ecosystems with unique species found nowhere else on the fragmenting supercontinent. The mammals that had survived in the shadows of the giant reptiles were also beginning to diversify in response to these changing conditions. While they remained relatively small compared to the dominant dinosaurs, they were developing increasingly sophisticated adaptations that allowed them to exploit ecological niches that were unavailable to larger animals. Some mammalian lineages were experimenting with arboreal lifestyles in the increasingly complex forest canopies that were developing in many regions. Others were developing semi-aquatic adaptations that allowed them to exploit the expanding network of freshwater environments created by continental rifting. Still others were evolving specialized diets and behaviors that allowed them to coexist with dinosaur communities without direct competition. The success of these early mammalian experiments was laying the groundwork for the evolutionary explosion that would occur much later, after the extinction of the dinosaurs. The insect communities that formed the foundation of many terrestrial food webs were also undergoing dramatic changes during this period of continental transformation. The evolution of flowering plants created new food resources and habitat types that insects could exploit in ways that hadn't been possible before. Some insect lineages developed increasingly sophisticated relationships with plants, including the early stages of the complex pollination partnerships that would eventually become so important to terrestrial ecosystems. Other insect groups were evolving in response to the changing vertebrate communities, developing specialized relationships with particular dinosaur species. The diversity and complexity of insect communities during the Middle Jurassic period was probably comparable to modern levels, though the specific species and ecological relationships were dramatically different from anything we see today. These communities provided crucial ecosystem services including pollination, decomposition, and nutrient cycling that supported the complex food webs developing across the fragmenting supercontinent. As we move toward the late Jurassic period around 150 million years ago, the effects of Pangea's breakup were accelerating at an unprecedented rate. The Atlantic Ocean was widening rapidly, creating an increasingly formidable barrier between the Americas and the Africa-Europe landmass. Other rift systems were beginning to separate additional continental fragments, including the early stages of the rifting that would eventually separate Antarctica from South America and Australia. The biological consequences of this accelerating fragmentation were becoming increasingly apparent in the fossil record. The dinosaur faunas of different continental regions were diverging rapidly, with many species now found only in specific geographic areas. The plant communities were also becoming more regionalized, with different continental fragments developing their own characteristic vegetation types that reflected their unique climate conditions and evolutionary histories. But perhaps most significantly, the process of continental drift was beginning to create the geographic framework that would influence evolution for the rest of Earth's history. The separated continents would continue drifting apart, carrying with them the biological heritage of Pangea, but developing it in new and unique directions that would eventually produce the incredible diversity of life we see on our planet today. The stage was being set for one of the most spectacular periods in dinosaur evolution as Earth entered what paleontologists call the golden age of these remarkable creatures. The late Jurassic period, beginning around 150 million years ago, would witness dinosaur diversity and ecological complexity reach heights that had never been seen before and would never be matched again. Picture the world that was emerging from Pangea's slow dissolution. The climate had stabilized into something more hospitable than the brutal extremes that had characterized earlier periods, yet it remained dramatically different from anything we know today. This was a world without polar ice caps, where lush forests extended almost to the Arctic and Antarctic circles, creating a greenhouse planet that supported life on scales we can barely comprehend. The sauropods that had been steadily growing larger throughout the early and middle Jurassic reached their ultimate expression during this golden age. Diplodocus, with its incredibly elongated neck and whip-like tail, stretched nearly 90 feet from nose to tail tip, while maintaining the surprisingly lightweight build that had made sauropods so successful. Meanwhile, Brachiosaurus towered over the landscape like a living skyscraper, reaching heights of over 40 feet and weighing as much as 12 modern elephants. But here's what makes this period absolutely extraordinary. These weren't just randomly oversized versions of earlier dinosaurs. Each species had evolved radically different body plans and feeding strategies that allowed multiple giant herbivores to coexist in the same ecosystems without competing directly with each other. Some species were perfectly optimized for ground-level feeding, using their massive necks to sweep across vast areas of low-growing vegetation like biological lawn mowers. Others specialized in high browsing, able to strip leaves from the crowns of the tallest trees where no other animal could reach. The success of these diverse sauropod communities created evolutionary pressures that drove the development of equally spectacular predators. Allosaurus, the apex hunter of late Jurassic North America, represented a completely different approach to carnivorous dinosaur design than anything that had come before. These weren't just enlarged versions of primitive predators struggling to bring down oversized prey. And so, as we return from this incredible journey through deep time, we can see that Pangea's story is ultimately our story. Every grain of sand beneath your feet, every mountain on the horizon, every ocean breeze you feel carries within it the memory of that ancient supercontinent. The extreme world of Pangea didn't just shape rocks and landscapes, it forged the very foundations of life as we know it today, creating evolutionary innovations that continue to influence every ecosystem on our planet. What other mysteries from Earth's extraordinary